Okay, so today we're going to be talking about a pretty simple model for machine learning. Perhaps it's even the simplest model you could think of, and that is linear regression. So as we talked about in earlier videos, linear regression is something you could use for regression problems, which is one of the two main types of supervised learning problems that we see. So today I'm going to be talking through how linear regression works, and also in general how you usually implement machine learning in a practical way. So first of all, how exactly are we supposed to train a machine learning model? Well, the first thing we need to do is we need to take our data and we need to separate it into what we call batches. Now, a batch is essentially just a smaller little chunk of our full data set. And the reason we do this is because if we don't do this, whenever we want to train the model would have to look at every single training example before it learns. And we'll get into what it means for it to learn in this context. But before it learns anything, it has to look at every single example. And typically, models learn in steps. And so this is a problem. So for this reason, we just divide it into batches, and this is especially useful when you have very large data sets. It could have potentially tens of thousands, maybe millions of data points. So this is a good start. So we divide it up into batches. And then what we need to do is we need some mathematical way of representing our model. See, often our model is just a mathematical function that takes in the vector of inputs, does something with those numbers, and can give you an output. So for linear regression, we're just going to make a pretty basic linear equation. So here we can see each of the vector values. So we have here, we got x0, we got x1, and then we have all of the different values are being multiplied by some coefficient, then they're being added together. And then over here, we have what we call a bias term. And this is just, if you were to write an equation like y equals mx plus b, b in this case would be the sort of y-intercept, essentially. It's just some constant that we add to the rest of the equation. So that's how we represent a linear regression model. It's just a basic linear equation, something you would see in algebra class. Okay, so that's pretty nice. But what do we do with all of this? Well, once we have this model, this representation, there's presumably some set of parameters. In this case, we call our parameters theta, and we represent them in a vector. There's some set of parameters that accurately predict our output. So you can imagine that each parameter is basically stating for every increase in x, the output has some effect. So in concrete terms, if we were doing a linear regression model that predicted housing prices, let's say one of our features was the number of floors in a house. So let's say x0 over here was how many floors a house had. Whatever theta 0 is, we're basically saying for every additional floor, the price of your home increases by theta 0. So that's one way of sort of interpreting the model. For every increase in an x, you have that theta increase in the y. So this will make more sense when you actually start making models, but that's one way of thinking about it. But the question is, how do we determine whether our model is accurate? Well, to do this, we use something called a cost function. So we represent cost as j of theta. That's our cost. And here we have y hat. Y hat represents what our model predicts. That is our prediction from this. And then we find the squared difference between our prediction and the actual value. We call this our cost. And given the fact that we've divided up our data set into batches, we say that we have m elements in a batch. So what we do is we go through each element in the batch, we find its square difference, and then we simply take the average of those, and we call this the mean squared error. So that's our cost function. That's how we essentially determine how good is our model. So now we have the model, we have a way of determining whether it's good, but how exactly do we reduce this cost function? What do we do about this? Well, the typical learning algorithm used across many different models in machine learning is called gradient descent. And here's a basic intuition for what it is. Now, if you've never done calculus before, or multivariable calculus, that's okay. I'm going to explain what all of this means. So, given some theta n right here, this is our weight, or a parameter as we might call it, we update each theta n. So we say theta n equals theta n minus the gradient times the learning rate. Okay, now let's dissect this equation. So this section right here, this is what we call partial derivative. So if you have a multivariable function, the partial derivative is essentially the slope at a point. Now what do I mean by that? Well, if we go down here, we look at what we've written out here. So here we have this j of theta plotted. Let's say we only have one theta. Let's forget about the multivariable part. You see this little red point right here. What would you say the slope is at that point? Well, the slope we call the derivative, which is just, you can think of this d as dy over d of theta. And think of d as a small difference in this case, it's an infinitely small difference, but think of it like that. So if we have some small difference in our x, we get this small difference in our y. That's our slope at this point. So what we do is we take theta and we calculate what is its slope at this point. So in this case, it actually has a positive slope. As you can see, it's sloping up. So we then subtract this positive slope from our current theta, which causes us to move left. And this makes sense because we want to minimize j of theta. This is the minimum j of theta. So because it's increasing, we go down because we want j of theta to decrease. If the slope were negative, since we're subtracting the negative slope, we would move forward. We would increase theta. Okay, does that make sense? So what you would basically do is you take the slope at this point, this gradient, and you descend the gradient. You go down to the minimum. Now you're probably wondering, well, what is this alpha term right here? Well, this alpha term is what we call the learning rate. So the learning rate essentially determines how fast or how big of steps you take. Now, one thing you need to be careful about is if you make your learning rate too large, we can get something called divergence. Here's what divergence looks like. Essentially, you overshoot the minimum. So let's say you have your theta is some distance from the minimum. We'll call that distance d. We'll call that distance d. Okay. So you're d away from this. After you make your gradient step, that's what we call these steps, afterwards we would say that your new distance is, call this d0, we say your new distance is greater than it was. And so because you're farther away now, you're going to make a bigger step and a bigger one and a bigger one. And you keep doing this until eventually your model is just unusable. It's completely worthless. And so this is why we want to avoid having too large of an alpha of a learning rate, because otherwise we get what is called divergence. So this is basically just the general intuition of most machine learning algorithms. You have some mathematical model which takes your input vector, does some computation, and gives you a value or a set of values. Then you have some function, in this case the mean squared error, that determines how accurate your model was, how well it's doing. Afterwards, we use some algorithm. In most cases, actually, it's gradient descent. There's many applications outside of just linear regression, including neural networks. We use some form of gradient descent typically. And what we do is we calculate the derivative, and then we start descending down the gradient so we can minimize theta, or minimize j of theta, for all of our parameters. And if you're not too comfortable with this whole descending down the gradient, this visual intuition for it, another way you can think about the derivative is the derivative is basically saying, okay, with our current theta, is j of theta going to be increased or decreased with an increase in theta? So we're saying at this point, if we increase theta, will j of theta increase? If that's the case, we want to decrease theta, of course, so that we can make the difference smaller. If not, we want to increase theta, so we can decrease j of theta. Does that make sense? Essentially, we're just looking at each parameter and we're determining how should we increase or decrease it and by how much. That's all gradient descent is really doing, and that's all you really need to understand. This is essentially all you need to really get started right here. So I hope this video was helpful. Next video we're going to be talking about logistic regression and probability models, and I will see you then.